and say good afternoon, good morning, wherever you are. Today is Wednesday, April 29th, and we are here for day two of the AGN Science Interest Group's Dissertation Jamboree. I'm Travis Fisher, part of the AGN SIG group. And we are here to hear two more talks from Payel Nandi and Yang Sun, who are going to be talking about research that they have performed, wrapping up or just coming out of their dissertation work. And before we get into that, I just wanted to share a quick slide about what we're hearing from the NASA folks as part of what we do or why we do what we do. So the Science Interest Group is part of the Cosmic Origins Program Analysis Group, which is called the COPAG, and they are putting out a retreat for SIG members, and we need to start working on, or they would like input on strategic mission concepts as part of the Astra initiative. And if you're not familiar with what the Astra initiative is, I have a QR code right here that highlights what that is. But what they're doing then is putting a workshop together in September, and then also looking for white papers on mission concepts moving forward. So what they've asked us to do is to provide names or concept ideas. So they're looking for individuals who have worked on or are working on new mission concepts, as well as folks that have contributed to decadal Astro 2020 decadal work on probe class concepts. Additionally, they're also just looking for relevant work that would be useful for the Astra initiative on AGN and galaxy evolution. So if you feel like you know somebody, or if this maybe applies to you, we'd love to hear from you. Please email either myself or Aaron Hicks as part of the SIG leadership, as we're looking to provide the COPAG, the parental umbrella of this SIG, with folks that maybe would be interested in joining this workshop that's happening later on this year. So again, if you're familiar with, either yourself or with somebody else that has done any sort of mission concept work, we'd love to hear from you. So thanks. And then, even though we are halfway through our AGN SIG Jamboree this week, we continue on with talks throughout the year, and our next talks after the Jamboree are starting in next month, where we have our monthly AGN coffee discussion group, which is on Discord, and you can get more information through this QR code here. And then we are also having our Vision Series talk later in the next month, where we're having Stephanie Junot giving a presentation on her work and talking about things with working out of NSF Noir Lab. So that is what's going on for your information. And then today we're going to be hearing from two early career scientists. We're going to hear from Payel Nandi, who graduated from the Indian Institute of Science in 2025 on the effect of AGN on ISM. And then we're hearing from Yang Sun, who is graduating later this year from the University of Arizona on the coevolution of supermassive black holes and galaxies. So, Payal, are you available to present?
Yes, can you
Okay,
hear me?
fantastic. I'm going to stop sharing then,
Yeah,
and then we'll have the floor be yours.
can you see the screen? Hello, can you hear me?
Yes, I muted myself. Yeah, yes, we can
Uh,
see the screen, and now there's your slide as PDFs.
yeah. So hello everyone. I'm Payel Nandi. I finished my PhD last year on the topic of AGN of effect of AGN on ISM of their host using multi in the multi-wavelength perspective. I did this work under supervision of Professor Stalin from Indian Institute of Astrophysics, and along with these wonderful people who helped me throughout my thesis. So, as this is the AGN group, so I don't need to introduce AGN, but just a quick overview. Like the AGN has the supermassive black hole at the center, and then accretion disk, and it surrounded by dusty torus and annular and BLR clouds. And from this AGN, the outflowing material goes from the center to the galactic scale, and these outflows are multi-scale and multi-phase in nature. It starts from the accretion disk as a wind, very high velocity winds, and then it propagates through BLR and up to the NLR's region, and then go to the galaxies. So in this schematic diagram, we can see some artistic view of different phases of outflows at different scale. Also, their observation tracer. In this thesis, my focus was to study this NLR-driven outflows, which are large scale. And normally, we trace through this outflows through ionized line by their asymmetric line profile. And these outflowing gas, when it propagate interact with its interstellar medium of the host galaxies, it can enhance the star formation, and we call that as a positive feedback. On the other end, it can stop the star formation itself, we call it negative feedback. So there are many studies, both in statistical ways as well as focused on individual sources, where people found the evidence of positive feedback. Here I have given one source, HE210, which is a dwarf hosted by dwarf galaxy, but the center there is a supermassive black hole. Here we see the AGN outflows are coming from the center, and it enhances the star formation in this region. So it is example of positive feedback, and there are any other example also. So we have also the example of a negative feedback, where this is the example of NGC 1167, where there is a jet in the center region, and in this region where jet started to bend, their high velocity disperse cold molecular gas is there. That means it is not a very good environment to form a new star. So this is example of jet mode negative feedback. In terms of these drivers of outflows from the individual studies, we have the example where the radiation or the wind from the accretion disk is driving the annular outflows, and also there are some sources where they found direct evidence of jet causing these outflows. In the statistical scenario, this is a kind of a small debate, as we know. So many statistical studies based on including STS's AGN itself, they found the radiation is mainly driving the outflows. But some studies like CSA sources, where the jet is the main mechanism, there also people found that jet is primarily impacting these outflows. So for in this scenario, it's like if there is radiation as well as jet present in some source like CFERS, where we see some kind of jet also as well as radiation, then what is causing the outflow? So that is not clear. With this, there are in this scenario of AGN feedback, there are few like not clear answer, like which mode of feedback it is happening, like jet mode or radiation mode. So it's more the current scenario is mostly it is radiation driven, but with the jet it is in the case where radiation is also there, that is not clear. And how this feedback happening, like whether positive or negative way. So from individual studies, there are separately we found example, but there is one source NGC 5728 where we see the both the evidence of positive and negative feedback, but at different scale. And what scale do we reach so far in the observation studies of this interaction outflow interaction, and this is mostly the few hundreds parsec to kpc scale, but the AGN HE210, there it was the smallest scale so far, like 75 parsec. And if we go to the more specific to the dwarf galaxies, so AGN feedback in dwarf galaxy, it is again we have like for individual studies only one source, which is HE210. But if we see in terms of black hole mass, like AGN, which powered by intermediate mass black hole, showing this feedback signature. So before this thesis, there was no such example was there. So in these by keeping this thing status in mind, I started my thesis by trying to address the sum of this question, like what drives the outflows, and then what is the impact of this AGN of the star formation scenario of their host galaxies. And in terms of a particular individual source, I started only one source, NGC 4395, which is a dwarf AGN. What is the nature of feedback there? And also what are the different phases of outflows exist for this source. So the first is what drives the outflows. So to start that, I took my AGN sample from SDSS MaNGA IFU surveys, where we had around 500 AGN. These are mostly Seyfarth's or liner type AGN. So our main aim here was to see the drivers of the outflows, whether it is radiation or jet. For to check that, we splitted our we cross-matched our sample in the first surveys, and we split it into two: radio detected and the radio undetected. And in the fundamental plane, like the redshift and luminosity, these two samples match to each other. We started by detecting outflows in these two samples by obviously seeing their broad wings in the ionized phase of O35007 line. And the result is here in this bar diagram. Like these are the total number of sources, and this dark region are for this fraction of sources we have detected outflows. So we found that for the radio detected sources, always the detection rate of outflows is higher. The number is 57%, and for the radio undetected, it is 25%, so less than half. And also we checked the kinematics of these outflows. So this is the histogram of the kinematic power of the outflows. We see the outflows in the radio detected sample are much more powerful in their kinematics than the radio undetected sample. So from here, the conclusion is that as these two sample radio detector sample, which is having radiation plus jet both, it has more occurrence of outflows, and the outflows is also kinematically strong. So that means the driving mechanism for these two sample is not same. There is something additional is happening in the radio detected sample. To check that, we checked the correlation of dependence of this outflow power versus the AGN luminosities. This is for the radio undetected sample. We see there is a strong correlation, and the steep this is the slope. And for the radio detected sample, also the correlation is much more stronger, and it became more steep. And for this radio detector sample, we have jet. So we checked how this outflow power varies with jet power. We see that it also very strongly dependent on the jet power. So from here, our conclusion is the radiation is causing the outflows in both the sample. Additionally, where jet is present, it is amplifying the strength of the outflows. Then our focus was to see the impact of AGN on the star forming characteristics. This is a different sample, and this is mainly the work using the UV data from the UVIT AstroSat. This is a imaging data imaging instrument on onboard AstroSat launched by India in 2015. And it has very good resolution of 1.5 arc second as well as field of view of 28 arc minute. So for nearby Seyfarths, we can really cover the whole galaxies as well with a good resolution. So my sample for these studies were the sources less than redshift of 0.01. and these are separate. So here the first part of work, it was the eight ciphers from the source, and which we can see here using the RGB image R-band from our HCT and NUV and FUV from UVIT. We first started to study the star, detecting the star forming region in the host galaxies of the Cepheid with this threshold criteria, and then to detect how many numbers of star forming region we are detecting and the star formation rate in this region after correcting for the extinction. So here, as we had both FUV and NUV, so we could use the beta slope method to characterize the internal extinction and correct that to calculate the star formation rate. So this is one example of NGC 1365, where we, after correcting the extinction, we calculated the star formation rate using the Koenig 1998 relation, and we plotted the surface density of the star formation rate of each clumps here, and we see that the region which are near to the AGN having high star formation rate. And if we remember this source NGC 1365 having nuclear winds along this direction, so we could see the high star formation in UV along these winds. And when we plotted this radial profile, the surface density of star formation rate decreased from the center to outskirt. So this is one example, but obviously this is not a universal pattern for our 8 sources in this study. Some sources we did not see this this radial gradual decrease in along the radial direction, but for four sources we could see this. And for to compare these sources, we checked the nuclear star formation rate, means again the surface density of the star formation rate in the nuclear region by taking 2 kpc diameter of aperture, and compare it with the total star formation rate by taking the R25 radius. So we see this star formation in the nuclear region for all these Cepheids are always higher compared to the surface density of the star formation rate of the as a galaxy whole. So that means in the nuclear region, always there is an impact enhancement of star formation due to this AGN at a 2 kpc scale. Then the next part is we focus to study this AGN feedback in much spatially resolved scale for a individual for one source, NGC 4395. This source is special in many cases. One is it is a low luminous AGN. You can see its volumetric luminosity is quite low, 10 to the power 4 arc per second, and it's a host by a dwarf galaxy of around 2 times 10 to the 9 solar mass, and it's powered by intermediate mass black hole of 10 to the 4 to 10 to the 5 solar mass. And the good point of this source AGN is it is quite nearby, just 4.3 megaparsec distance. So that means 1 arc second equivalent to 20 parsec. That means if we have the resolution of 0.1 to 0.5 arc second, we can really probe to a sub-parsec scale to check the AGN feedback in this source. When we start working on this source to check its nature in the center region, we see this is the AGN blob, and this is the UV, how it looks like in UV. We can see there is a very high star forming clump which is around 100 parsec from the region, and it's connected to this filamentary structure. And from our UV and H alpha studies, we found this is having high SFR and younger in age and low metallicity. And that means there is a probability that this enhancement of star formation in this region may be fueling due to some AGN activities. Through AGN activities, to check that we looked into the ALMA data through the CO2 to 1 transition to trace cold molecular gas. We found that this source having the cold molecular outflows, and these outflows from our PV diagram we confirm that this source is having outflows and it's reaching up to the S blob. So the cold gas from the nuclear, it's feeding actually this blob which is having high SFR. So at this 100% scale, this AGN is feeding the star formation here. That means the positive feedback at this scale. And this is the line profile of this three region of CO2 to 1 line. From here itself we can see gradual the nuclear has very asymmetric with 3 component, and this intermediate region B and then final destination of S is gradually following its blue shifted part. So for this is just a schematic of AGN outflows and feeding the star forming blob here. Then we probed this central region which much higher resolution data. And if we zoom into the center region from this schematic, we can see that we have BLR and then NLR region, and along this direction we have polar dust in this ionizing cone. And here in the NLR, coming from NLR inwards to the BLR itself, there is some ionization gradient is there, and the molecular outflows is in this direction. And this ionized outflows, it can goes up to few hundreds electron volt. We can trace through optical and infrared spectra. So when we take this source in terms of outflow space, not only the molecular or ionized space, we could detect both hot, cold and hot molecular outflows for this source, and also in the neutral lines, as well as more than 30 ionized line. By combining optical and infrared IFU data, we could see the presence of outflows starting from 7 electron volt to 300 electron volt. A gas is present there. So here I have shown only 3 such example. More can be seen in this paper. So outflows in this source is present in all phase, molecular, neutral, and in a whole range of ionized gas. So then, as we had more than 30 ionized line detected in this source with ionized outflows, so we checked their the efficiency of outflows in terms of the total luminosity of this line, how that varies with ionization potential. So before we had this kind of few plots from other studies, but there were data taken from other source, or for single source maybe 4 or 5 points. But for this we have more than 20 or 30 data points here, and we see that as ionization potential increase, the efficiency or the fraction of the outflows is actually outflow luminosity is increasing. And we also checked its outflow velocity, but it is not any nice pattern we could not see, but initially we can see there is a increasing trend, and after that it is not following. So from here it's like we can see this and from here if we see the high ionized outflows means they are lying in the inner side of the NLR region, which sometimes we call coronal line outflows. So they are having high luminosity, but when we calculate its efficiency on the feedback, we found the lower ionized outflows are having more feedback efficiency than higher ionized outflows. Then coming for the sort of time, I'm going back to going to the spatial studies of this source. So when we mapped the ionized gas from O3 lines, which is around 36 electron volt gas, we see this is asymmetry in the morphology itself. So from this asymmetry, we can expect the outflows kind of biconical. And when we checked its radio early at 15 gigahertz, we see this jet-like pattern, and it has the central component, and there is eastern side of the jet and the western side of jet. From this asymmetric in the both radio morphology and the ionized gas, we concluded that this is we are seeing the interaction of jet and ionized gas. We then checked the kinematics in this spatial of all these pixel in this region, and just remember these are only we are seeing around 10 parsec scale, which are kind of NLR scale itself much smaller. So the eastern side of the jet, where the jet was more strong, there actually we are seeing more dispersed gas, as well as their asymmetric index is higher. So here actually we are seeing the jet is enhancing the outflow kinematics itself. It is just one special example. And we also checked the presence of ionization here, whether there is presence of shocks or only these are photoionized. So it is very difficult because we are just seeing 10 parsec scale, but with help of mapping 3, we tried to constant here. So we see this these are the our data points, and these are the grids for the age for the dust free AGN. So these are very close, but not exactly lying. But when we checked the soft model, actually the pixels in this whole region were nicely follows the soft model. But the gas, the points which are having like in the eastern side in the more jet, they are actually lying in the higher velocity is a gas. So the jet where it is more powerful, there is like high velocity shocks is present there. So in conclusion, for this NGC 4395, we see the central engine and sorry, we don't see the black hole obviously. So from the intermediate mass black hole, there is a jet, and there is a multi-phase gas is here, like hot gas, molecular neutral gas, as well as both molecular gas in cold and hot phases. And these ionized gas, they are not able to go beyond this 10 parsec scale, they are stuck there. But this cold molecular gas actually that is flowing and reaching up to 100 parsec scale and feeding this blob which is present there and enhancing the star formation activity. So this is the summary of this four thing I presented, which is my part of thesis. So I'll just stop here, and thanks for listening. I'll take question.
Payel, thank you. Many applause, explosions of applause. Fantastic.
Thank you.
If you have questions, why don't we raise hands? Use our little, what was the chat? Someone had a question in the chat, maybe. Mingy, do you want to just ask your question?
Sure, my question is very simple. When you measure the star formation rate from the UV, how do you correct the dust extinction and the dust attenuation in a UV? And is there any different treating, between the host galaxies and the nuclear region?
So is I think I just mentioned one line, but I talked a swim speed. So here, when I'm starting the star formation, I remove the nuclear PSF. So here, though in this plot, it's like for this clumpy, it is in the 0, but there is no AGN here. So we remove the 2 times aperture of PSF. So, but the next part is for the internal extension. So we have this beta slope method. Means if we have FUV and NUV part, then we calculate the luminosity, we can calculate the beta, and from there we can get the internal dust extension values using the Cal-Zetis relation, and I've just corrected using that.
Okay, thank you.
I had a question myself. So one of your earlier conclusions was that a lot of the outflows that you're seeing are radially driven, but are then accentuated, I guess, by radio jets and whatnot. Can you speak more to that in how we can confirm that these are radio jets versus them being like a shock signature potentially? Because what you could also maybe be seeing then is just the winds are running into that host material and creating those shocks, and that's the mechanical feedback here. So could you speak more to that?
Yes, so that is like, I'm not very much sure about whether these are jet, but one thing is that when I checked this morphology of these sources, so they were like in the fast resolution, obviously 5 arc-second, these are mostly like a kind of compact sources, except like few maybe less than 5 are having large scale like KPC scale jet like features. But I cannot distinguish between this radio emission. Really, they are shocks because these are just on radioluminosities. So here the approximation was we are seeing the jet contribution. Yes.
All right. I don't see any more questions. And Kevin Zhang has a quick question about the positive feedback. How do we know AGN is driving this star formation blob using the CO molecular gas as a tracer? And this will be our last one.
Yeah. So here this three work I just showed in very small this way. So here, if you can see, this star forming blob is found in UV and H alpha, that, and we also had this source having the MaNGA IFU. So from there we could confirm that this blob is not really the ionized by AGN. This is a star forming blob, so that is not AGN ionized. Then when we checked the molecular gas flows, it's actually flowing from here to here. I think here it is. Here we can see. So it's like gas is coming from here and reaching up to here. So from here, I think it's clear. And you can ask more. Like, I don't understand like the doubt actually, because in the spectra itself we can see like its velocity is propagating from here to here. Like, this is the spectra of A's blob, this is the B, and this is the nuclear, which is having our component. So the PB map I have not shown here, but I thought it is clear.
Thank you. Okay, thank you very much again for an excellent talk, Payel. Of course. Okay, so then our next speaker today then is Yang Sun from Arizona. And Yang, yeah, perfect. Fantastic. We'll just let you jump right in then.
Can you hear me now?
Yep, can hear you now.
Okay, let me reshare my screen. Can everybody see it?
Yep.
Yep. Okay, sure. So hello everyone. I'm Yang Sun. I'm a fifth-year grad student at University of Arizona. So thanks for giving me this opportunities to share my thesis work, which is titled with coevolution of supermassive black hole and galaxies from cosmic union to the present days. So over the past few decades, we have known that the supermassive black hole and their host galaxies co-evolve together. So one of the most striking pieces of evidence is this strong correlation between the black hole mass and the host galaxy properties. So in the left is the stellar mass, and also in the right, when we turn into dynamical mass traced by stellar velocity dispersion, the relation can be much stronger. So even though such strong correlations has been determined, we still don't have clear understanding on like what kind of physical mechanisms driving their coevolution, how their coevolution firstly emerged in the early universe. So basically, there are two main possibilities. The first one is simply the hierarchical gas assembly. When galaxy merge together, they are naturally linked. The central supermassive black hole and the host galaxies grow together without any additional physical coupling. And the second one is the AGN feedback, which really is a physical process linking the central supermassive black hole accretion, and it can drive strong winds and outflows and radiations to impact the surrounding ISM to further regulate the star formations and supermassive black hole accretion in a later on. So to really understanding the whole picture of supermassive black hole galaxy coevolution, there are basically two approaches. The first one is through the integrated view. We can study the mass scaling relations, see when and how they emergence and how they evolve with cosmic time to know from the statistical view to know their pace of growth. And the second one is directly zoom into the galaxy systems to learning their physical mechanisms like AGN feedback to study how exactly the supermassive black hole impact the galaxy. So my thesis work is centered around these two topics. So first of all, I will talk about the mass scaling relation, and later on I will turn to AGN outflows and their impact on galaxy quenching. So for the mass scaling relations here, I'm showing you what people have been learned before JWST launched. So here the y-axis is the black hole mass versus stellar mass, and x-axis is the cosmic time. So before JWST, such evolution studies can only reach to like redshift 2.5, and even at this epoch where we right now just call it intermediate redshift, there was no consensus for a long time. So some people claim the black hole to stellar mass ratio has significantly grows towards the higher redshift, but somebody says it's keeping it as a constant. So such a discrepancy is mainly due to two factors. The first one is the observational biases. So especially at the higher redshift, when we have a flux limited surface at a given stellar mass, you are more easier to observe agents with brighter luminosity and thus higher black hole mass. So naturally bias your observed black hole to stellar mass ratio to the higher end. And the second one is an appropriate choice of the local benchmark. So as I'm showing here, in a local universe, if we're just looking at the local AGN host, their black hole to stellar mass ratio are intrinsically lower than the early type galaxy because the local AGN hosts are usually more late type disky galaxies. So if we just simply compare with the local AGN relations, you would easily get the conclusion of width evolution. But once we take all type of galaxy together, using all type relation, like from the Green 2020, it ends up with there's almost no evolution of the mass scaling relation up to redshift 2.5. But then with JWST, one of its most spectacular findings is the faint agents and also bright quasars above redshift 4. So now we are able to measure the black hole mass to the fainter agents at high redshift universe, and also study the quasar host. And surprisingly, we find both the faint agents and quasars above redshift 4 seems to have higher black hole to stellar mass ratios, way above from the local relation. So it naturally brings up a question, like if we don't see a significant evolution of scaling relation up to redshift 2.5, but then above redshift 4, there's a significantly higher ratios compared to the local one, then does that mean there's a dramatically change happening between redshift 2.5 to 4? So to answer this question, one of my thesis work trying to fill in this redshift gap by building up a new broadline AGN samples at redshift 1 to 4 using JWST, near-camp wide-field slitless spectroscopic survey, Fresco, and Congress. So we search for broad near-infrared line, Gaussian alpha, beta, and helium-1 in these two surveys, which is targeting the good south, good north field. And by requiring full width Hubble maximum of those lines should be above 1,000 kilometers per second, we identified 18 broadline agents at redshift 1 to 4, and among them 8 are beyond redshift 2.5. So with the line width measurement and also the AGN bolometric luminosity, we are able to infer a single epoch viral black hole mass. And for the stellar mass measurement, we are using the AGN host galaxy decomposition method in their JWST imagings. This method can eliminate the AGN contaminations when modeling the host galaxy light, and thus which can induce significant large uncertainty on stellar mass measurement. So as this bottom line shows, we model the light profile using one PSF and a surface, and PSF is for the AGN light, surface is for the host galaxy. And we do such decomposition for 7 near-camp wideband images, and we can get the host galaxy as CD and then infer their stellar mass. So here I'm showing you our new broadline AGN samples at cosmic nu and their positions in the mass scaling diagram. So they are shown by the yellow stars. As you can see here, the observed black hole to stellar mass ratio for those cosmic nu broadline agents are already consistent with the local relations, even before we accounting for their observational biases. But even so, we still build a comprehensive observational biases simulations to trying to understand how much the observational biases as well as the mass measurement errors could bias our view of the black hole versus stellar mass distributions. So our simulations is simply ask a question: if the AGN population is still follow the local relation, then how would their observational biases and also the mass measurement errors reshape their distribution from their intrinsic one to what we observed. So from the left to right here, we first build a mock AGN distribution, will follow the local relation. And then we add on the mass measurement errors. So you can see in the middle panel, the distribution slightly broadened than the intrinsic one. And finally, we applied for observational biases. So here includes two parts of biases. The first one is a line detection flux limited from a designed gradient survey. And any agents below that, that flux limited would not be observed. And also the second one is a line width cut. Any broadline agents with line width smaller than 1,000 kilometers per second would also not be identified as broadline agents in our approach. So you can see finally in the right figure, the predicted observed distribution indeed tilted up, especially at the low mass end from the intrinsic distribution, indicating that the observational biases and errors can significantly bias our view of the black hole mass versus stellar mass ratio. So now with such a simulation, we can compare the predicted distribution with what we truly observed. And as this panel shows, it already showing you that the observed samples are well enclosed by the predicted distribution pretty well. But then our simulation is moving one step forward. We are not just simulating the overall identical the distribution of the observation. We are also asking whether the observational biases and the measurement errors could also predicted identical observable agent number counts as what we observed. So simulating a true observation surveys. So to do this, we need to add on two more informations. The first one is a survey area to simulate the underlying AGN and galaxy population size. And another one is an empirical broadline AGN fraction, because not all galaxies have an ongoing AGN and not all AGN are a broadline AGN. So after adding these two informations, in the right-hand side, we are comparing the number counts between the simulation and observation. You can see they are matched very well. And also at the same time, the black hole to stellar mass distribution are also consistent with each other. So indicating that the cosmic new broadline agents are consistent with the local relation without any needed to introduce significant evolution. But then the question is, okay, if the mass-scaling relation doesn't evolve up to redshift 4, but we indeed see a significantly overmassive agents above redshift 4. So what's going on there? So another paper I worked is simply applying the same simulations I developed for the cosmic new surveys, but then to the higher redshift agents to ask whether those JWST newly discovered fan agents and also quasars could also be fully fully explained by their observational biases without a significant cosmic evolution. And I don't have time to dig into the details, but the main takeaway is that we find the fan agents seems to be significantly significantly higher than the local relation. They cannot just simply explain by the bias or the measurement errors. But for the quasars, considering their very large observational biases, they seem still more or less consistent with the local relation. But to fully constrain the format of the mass scaling relation above redshift 4, we really need a statistically larger sample. And also, if those high Z agents is intrinsically overmassive, then how they evolve back to the local relation at a later epoch, how their hosts grow faster and catch up their initial black hole goals is also important questions we need to answer in the future to have a full understanding on the supermassive black hole galaxy convolution picture. And now I want to zoom into my second topic, which we will touch on the specific physical mechanisms really link the supermassive black hole and the galaxy, which is AGN outflow, and understanding their impact on the galaxy quenching. So people have been long thought that AGN feedback is the key mechanism to driving massive galaxy quenching, transiting them from the star-forming main sequence to the red dead galaxy populations. And as this beautiful outflow cartoon shows, the outflows can significantly impact the ISM by either directly ejecting them to the CGM scale or maybe hit it or disturb them to prevent from the future star formation. But we still don't have clear understanding on how outflows participated in galaxy quenching, like when does it launched, how it maintain or drive quenching, and also more important question is whether star formation or AGN feedback, AGN is the key mechanisms for the outflows. So the pathway, I think, to answer this question would be to looking for the outflows across the whole evolutionary sequence from the star forming to the quiescent, especially to the galaxies at the quenching stage, to understanding how does outflow behave across this evolutionary sequence and also their impact on the quiescent galaxies, star formation. So to look for the outflow signatures here, I'm focusing on the sodium doublet, which is tracing the neutral phase of AGN outflow. So this phase of outflows can be easier achieved, especially at the quiescent galaxies compared to the well-studied the ionized phase like the O3 trace outflow, because in the quiescent galaxies, they are usually lack of nebula emissions. So to looking for the ionized phase would be a really severe problems. So we looking for the sodium doublet, which is tracing the cool neutral ISM. And by modeling both the stellar contribution and also the ISM contributions, we can characterize their velocity offset and also the optical depth to understanding how many outflowing mass is carrying on and whether it's outflowing or inflowing by study their velocity offset. So as you can see here, this technique, since we are targeting on absorption features, it really needs a high quality spectra which has good detection on the continuums. So before JWST, such of studies can only be done at the local universe. So here I'm using the Sloan service. We build up a comprehensive evolutionary sequence from the starburst to post-starburst and quiescent in this H alpha equivalence width versus H delta absorption diagram. So we studied the sodium doublet outflows in 3 different galaxy populations and to see whether they have any trends across this quenching sequence. And indeed, in the right-hand side, I'm showing you that we find both the neutral outflow fraction and also the neutral outflow velocities are decline together along this sequence from the starburst to quiescent. And even when we zoom into the post-starburst phase, we also find the velocity offset is decline along with post-starburst age, which is the time since galaxy quenching. So it tells us the outflows, neutral outflows, indeed are strongly coupled with this rapid star formation decline sequence. And furthermore, when we plot those outflow detected galaxies in the BPT diagram to see, to identify any AGN features, we indeed find those outflow detected post-starburst galaxies preferentially located in the Seaford region, especially for those outflows with fast enough outflow to escape to the CGM. So such a strong AGN fractions in fast quiescent outflows in local universe already suggest that there must be a connection between the AGN-driven outflow and with this rapid quenching pathway. And now with JWST, we are able to extend such sodium doublet outflow studies to a higher redshift. Using the same outflow diagnostic, we can do fair comparisons of the AGN outflow behaviors across cosmic time, and also understanding how does it drive the first population of galaxy quenching at the peak epoch of our universe. So we compile a very large near-spec samples from 4 JWST surveys, and our parent sample includes about 300-ish galaxies from redshift 0.6 to 4, and their distributions of the stellar mass and the subformation rate is shown in the right figure. They are all modeled by the SCD fitting. So among those 300 galaxies, we detect 76 76 galaxies with sodium doublet ISM. And you can see the detections are mostly located at the massive end across a wide range of specific star formation rate. Even though in this census work, we talked a lot about the sodium doublet ISM incidence and how it depends on the host galaxy properties like the dust and also the star formation histories. But for this talk, I want to specifically focus on the sodium doublet outflow we see at cosmic noon. So the most important findings we have from this work is we find the sodium doublet outflows driven mechanism seems to be different in star forming galaxies and quiescent galaxies. So here in 3 panels, I'm showing you the 26 sodium doublet outflows we detected, and the red are those detected in quiescent, and the blue are in star forming galaxies. So we see that we have see very strong correlation between outflow velocity and the specific star formation rate, but only for star forming galaxies. There's no correlation at all for the quiescent outflows. And the second thing is that when we compare the outflow energy rate with the star forming luminosity or the AGN luminosity, we find those outflows detected in quiescent generally exceed the maximum energy that could be provided by their current weak star formation. While since most of them, about 60% of them have an ongoing agents, and then we compare their outflow energy with the agent energy, we indeed find those outflows could be explained by their current agent activities, which is more or less located below the maximum energy expected for agent-driven scenario. So that means that we think the outflows in star forming galaxies is still mainly driven by their current star formation, while in quiescent, they must be contributed by the agent activities. However, we still find among our 16 quiescent outflows, there are 5 outflows are hosted by quiescent galaxies without agents. So in other words, it means that those outflows cannot be explained by neither their current star formation nor their nuclear activity. So what's going on for those outflows? So we propose a agent fossil outflow scenario, which meaning that those outflows are driven by their past agent activities while the active phase has already turned off, while the launched outflow is still visible. So such agent fossil outflow has been proposed by many agent outflow simulations, and it's also making sense when we do a simple timescale comparison between the outflow and the agent activities. So considering the outflow traveling from the galaxy center to the extent we observed, and also its velocity is about 2 million years for their traveling. And such timescale is much longer than the typical episodic agent activity timescale, which is only about 0.1 million years. So indicating that during outflow traveling, agent can already turn on, turn off many times. And so that's not surprising that we are capturing some outflows in a specific time moment that their past agent activity has already been shut down. And it also indicates that agent feedback can be long-lasting. It can persist far beyond the activity phase, and thus it may suggest those agent fossil outflows can help maintain the galaxy quiescent, even when the agent activity has already faded. And finally, we also, similar as what we find for the local universe, we also see the sodium doublet outflows are preferentially detected in quiescent galaxies with younger age, with lower d4000 break, as well as the higher H delta equivalence width, meaning that they are in young, rapidly quenching galaxies. So such a preference in the post-starburst phase may also indicate those outflows may have a contribution on this unique rapidly quenching pathways. But all in all, to really understanding the connection between the agent feedback and the galaxy quenchings, we need to have a much better understanding on the outflow behavior through a spatially resolved view, and also we need to understand the time scale between the AGNs, outflows, and quenching because they can be very different. So in the future, I will continuing to study the spatially resolved outflow studies in the quiescent galaxies and also zoom into their molecular phase, which is more direct view of the star formation to really understanding what's going on for the AGN feedback on galaxy quenching and cosmic new. So that's almost all the things I want to share today. So I will leave my takeaways here and take any questions.
Fantastic. Thank you so much, Young. So much applause. Do we have any questions on all of this amazing work? While people are thinking of things. So part of what we're trying to do is come up with ideas for what we need to be doing with mission concepts, as I was talking early at the beginning of today's presentations. What do you think that we would need to help continue this work moving forward?
Sorry, could you repeat your
Right.
question
So
again?
just for like mission concept work,
Mhm.
like what would help answer or solve some of these questions that you're still having here in terms of like observational capabilities to be able to continue solving these problems? So, like, mission ideas.
Yeah. So the key idea I right now have on my mind specifically for the AGN outflows and also AGN quenchings would be that we really need a larger statistical sample of spectroscopic observations for the high redshift AGNs and also the quiescent. So right now, with only JWST and considering how popular it is, and also its very small field of view, we are really just limited to our view on some legacy field with very limited high quality spectroscopic observations. But as you can see here, for really probing the AGN outflows, the quiescent, also constraining their self-formation histories, we really need very good spectra to capture their stellar population features and also the outflow signatures. So I think that's
And this wouldn't be
probably
something like Roman, because we would need longer wavelengths than that, right?
but since Roman only have if I remember correctly, like the prisms or the prism mode, which are not, I would not say very powerful to probing the quiescent at like redshift beyond cosmic new.
Hmm.
So it would still like definitely it will increase in the sample size, but still limited in the nearby to the cosmic new universe. So yeah.
All right, Mingy, you had a hand up first.
Yeah, I have a quick questions about regarding those overmassive, supermassive black hole in high redshift. You do the host galaxies and I mean component decompositions, two decompositions, and you have the bulge component. Can you just tell me what's the Cersei index of those bulge component for those
Yes.
over?
So
Yeah, yes. I just
yeah.
seen
So
the here. I mean, I don't know the number, but I'm curious about the number. This is
no,
my
no,
quick number questions.
no, you're good. So unfortunately, we cannot resolve the bulge components for
Hmm.
any of our the cosmic new broadline agents. So
Hmm.
and also here, so we only applied one surface model to model the whole host galaxy light profile, and we find for our 18 broadline agents, most of them have surface index around one each, so mainly still tracing the disk component.
Okay.
So it's really hard to see the central bulge component, which in principle should be the the most direct components to link with the central supermassive
So the
black holes.
disk is still
Yeah.
around 1, right? Around 1.
Yes. Yeah.
Okay.
Yeah.
Great. So thank you very much. Thank you.
Yeah.
Pallavi, you got a hand up?
Yeah. Hi, Ang. Really great and impressive work. I have a question about the fossil outflow slide that you talked about, and
Mhm.
just in general, the AGN selection that you have. You
Yes.
mentioned that the fossil outflows can last much longer than the AGN activity. So my question is,
Yes.
have you done cross-match to see if any of your sample has radio source associated with it? And the reason I'm asking is because radio jets are powerful enough to, they last much longer than just radiative AGN activity, and they can drive these outflows to kiloparsec scales. So just
Yeah,
curious.
so that's a really great question. I think I don't pay too much attention on the radio part. So currently my agent diagnostics is just crossing X-ray to optical and to the mid-infrared dust torus emission. Some of my good cells targets within the central ultra deep field. I think so. One of my collaborators, Jianwei, maybe you know him. He's doing the multi-wavelength agent diagnostic, and he tells me at least for my good cell sample, there is no like significant radio sources. So, but indeed, I will go back to check like any of them have radio counterpart. Yes, that's a really good suggestion. Thank you.
Thanks.
Kamen Zhang asks in chat for the overmassive issue, some people think it's due to the different dust obscuration in early cosmic time. Also, there's a paper earlier this year about electrons scattering to artificially broaden the emission lines. How do you think about those explanations?
Yes, so that's a really important questions, and also it links to biggest mystery that JWC finds so far, which is called little red dots. We don't know whether those sources are truly or typical broadline agents. We know a lot from the local universe. So indeed, people find their broadline profile seems not truly be like Kepler Gaussian profile. They may be electron scattering showing some exponential profile. And so I agree with that. And I indeed think people need to pay much more attention on when people say broadline agents at high redshift, that whether they are typical things or they are more little red dot unknown sources. And I indeed think people are right now trying to distinguish the typical type 1 agents and also the little red dots. For the typical one, I think people finding that their profile seems to be still consistent with what we know for the typical type 1. So their black hole mass measurement should be okay. But for little red dots, I definitely think that's an issue there. And yeah, that's an issue.
Okay. They say thanks. All right. If there aren't any other questions, then I guess we will call it a wrap today. Thank you very much to both our speakers for taking time